Good afternoon, everyone. I must start by saying that I'm well out of my depth here because, a lot went on in this presentation and the ones earlier, it kind of goes way over my head. We're going to go back to physics and particularly the stuff that we cannot control digitally with our desks and other equipment. I'm a lecturer at the university. I work in the Acoustics Research Centre. I've done a bit of research with the guys at BBC R&D in Manchester. Of course, they're quite close. And I've also participated in the S3A project that Marcus was talking about earlier on. So that gives you a bit of context. Okay, so what am I going to talk about? I'm going to talk about room acoustics in general to start off, just give a bit of background about behavior of waves and how they kind of make the sound that we hear. We'll then move on to looking at room design and what are the tools available to cure acoustic problems in the rooms that we use. And I'll then spend a bit more time looking at the low frequency part of the acoustic response in these rooms. And I hope to kind of transmit that that's still one of the key areas that needs improvement. Okay. So first of all, a bit of context. We're obviously talking about rooms that we use to either record sound. You've got a bit of a plan of a recording studio on your left where you can see places where you would record instruments and a place where you monitor the sound that you're recording. That's going to be, of course, very important. Most of my talk, I will concentrate on stereo monitoring, but a lot of the stuff that I talk about applies also to, surround type of systems. Of course, you would need to adapt the design decisions for that. Now, one important thing is to realize that when we talk about sound, we're actually talking or using a wide range of sound sizes. What do I mean by this? I'm kind of referring to the wavelength of sound. And I'm sure many of you, if not all of you, will know that the wavelength of sound varies very widely across the range that we can hear. So we can hear between 20 hertz to 20 kilohertz. And because the speed of sound, airborne sound, is constant, then the wavelength changes to accommodate for that. So if we're looking at low frequencies up to about 200 hertz, then usually in simulations, in studying the sound, we have to keep things wave-based. So we study the sound as a wave that propagates away from the source. If we go to the higher frequencies, because the wavelength is much, much smaller, then we can start looking at where sound reflects from a certain boundary. So we can define the reflection points a bit better than we do for low frequencies. Just to give you a bit of an idea, the lowest frequency we can hear is 17 meters long. That means that it kind of fits almost nicely into this auditorium. But if we move into a room, a control room like the one in the back, then that wave is actually larger than the room itself. So it will interact with the room in specific ways. We'll look at that later. So here's just an example of how we can represent sound behavior. So we've got a source, and then that source kind of generates a spherical wave that propagates away. As that wave encounters a boundary, then it gets reflected. And in acoustics, we can actually simulate that by inventing another source. We call it an image source, which is on the other side of the boundary. And that image source generates a spherical propagating wave in sync with the original one. And as they interact with the boundary, we get the reflections. Now, I can use this type of idea to then find out what would be the kind of sound behavior if I had a source, a boundary, and then a receiver. And this is important. We need a receiver to be defined in order to use this idea of sounds as rays. But if I do that, then I can say that I've got my source, I've got my image source, and if I trace a line between the image source and the receiver, where that line crosses the boundary, I know where the reflection is going to be. And as a practical use, you can actually do that in a studio where you've got someone sitting at the desk, someone else with a mirror, moving it alongside the wall, and if the operator can see the speaker, you know that a sound is going to, the first sound is going to reflect from that. So we talk about reflections of sound and we talk about orders of reflections, first order, second order, and so on. And that has to do with how many interactions with a boundary a particular sound wave has. So Here's an example where we use the same idea of image sources. In this case, I'm just presenting the first order image for all of these boundaries. It's basically a room seen from the side. I can define a receiver position, although that doesn't quite matter for this simulation because I'm still showing the spherical waves propagating. But as soon as I've got a system like this, I can actually change it to trace the rays of sound for this particular source-receiver room combination. And that allows me to then see how the sound interacts with the walls, where it reflects, and eventually it gets connected at the receiver. And as I said, we can talk about sound in first, second, third order reflections, which are just kind of folding out the room into more and more orders. And you can see that we've got this propagation of sound and of reflections eventually being connected at the receiver. So if I use that idea, I can actually define the response of a given source receiver and room system in terms of how it develops over time. So I know that the first sound is always going to be the direct sound unless there's a, something in between. But then I see all of the reflections appearing, and I can plot them over time and see that if my original sound is an impulse, then I'm going to have just copies of that impulse arriving as we go over time. And I know that in rooms, we can talk about this early region of behavior up to about 10 to 20 milliseconds, to which we call the early reflections. And these early reflections tend to be really important for our perception of sound in these small rooms. After that, we start getting reflections appearing from all other directions, bouncing off in the late stage and arriving very quickly all together sometimes and from all directions. So they're slightly different. And to this we call the impulse response of the room. Okay, so as we move into room design, how can I use some of this knowledge to apply some treatment to rooms to try and cure some problems? Well, I've just mentioned there are problems. So what kind of problems do people usually deal with in these situations? When you're looking at room design, and I'm kind of focusing on control room design, the cubicle, as someone mentioned earlier on, but it's basically where you monitor the sound. But some of these techniques are also applicable to the recording space, of course. So what kind of problems do we usually find? Well, if the room is completely untreated, or if you've got parallel walls which are bare, then you will probably find that there are some flutter echoes, and I'll give you an example of what that is. You also need to focus on this idea of the initial time delay, really important term there, and you obviously need to design for good image control, in this case, stereo image control. And if I have time, I will then move on to the room modes, the low frequency part. Okay, what kind of tools do we have available for this? Well, of course, everyone knows about absorption and that you place kind of soft materials on the walls and they tend to absorb sound. It's important to know the relationship between the depth and the actual composition of that material and the wavelengths that you're trying to absorb. For instance, for low frequencies, the wavelength is so long that a simple thin absorber would not work at all. Okay, so we need to know about that. But there are other tools. So for instance, we can splay the walls and kind of redirect reflections which would hit the listener, but we can redirect them so that they kind of move away past the listener without hitting where the listener is sitting. And of course, we can also make complex surfaces like the ones we have at the back of this auditorium, which will tend to diffuse or scatter sound. Okay, so here's an example of a flutter echo. So a flutter echo happens when you've got pairs of parallel walls which are bare, which have no treatment. You'll look around this room and you'll see that most of the surfaces have got some treatment in them. If they didn't, we'd be suffering from flutter echoes in here, although many of the walls are also splayed, which tend to cure this. So let's have a listen to this. We'll need sound now, please. So hopefully you can hear that kind of thrill at the end of the snare. It's going to repeat. Kind of repeats. So this is basically a train of echoes that appears in the impulse response. And we can cure it quite simply by just placing absorption in such a way that you never have pairs of opposing surfaces. You don't want to put too much absorption because that deadens the room. So you basically just try and break these paths. And if you do that, then you recover your nice sound. Okay. Another problem that you often encounter is the idea that if you're in a control room, you want to listen to what you're recording in the live space. The live space itself has its own acoustics, and we can talk about the initial time delay of the live space, the distance in time between the arrival of the direct sound and the first reflection. If in the control room we have earlier reflections that arrive earlier than that time, then we have no chance of actually listening through to the live space. So a good design process is to actually try and abate these reflections here. How could we do that? We could use one of the tools that I've just mentioned to you. I've got an example here on the left. This is the control room before treatment. And what we can see is that after the arrival of the direct sound, I've got a side wall and a floor reflection, a ceiling reflection, and even in the later time, I've got a lot of sparse reflections, very well noticeable reflections. That wouldn't sound very good. And it certainly wouldn't obey this idea that we need to have an ITD in the control room, which is longer than the live space. This is after treatment. It's used the reflection-free zone, which is basically redirecting reflections. And we can see that there's a really nice gap where we can listen through and actually listen to what's happening in the live space. And as a bonus, we actually get a really nice decaying behavior of the energy in the later part, which sounds a bit more like reverberation, which is a bit more benign for studios. And then finally, I kind of talked about controlling the stereo image. Now, this is really important because we know that in stereo, we operate within the summing localization region. That's where we have 2 copies of sound arriving at our ears within about 1 to 2 milliseconds. If that happens, we perceive a phantom image in between the speakers and not 2 sounds. If we then allow to have another reflection, another copy of the original sound arriving from the side walls, then that's going to play about with our hearing system, and it's going to make us perceive like, you know, the things have changed somewhat. So if this reflection is within 0 to 2 milliseconds, we're going to get an image shift of the sources that we're trying to pan with our system. And of course, we could use redirection, absorption, or in some cases diffusion to try and treat that. So how does this then feed into these room design philosophies? And there's a number of them that have been published in some literature in the past. I've just brought a couple of examples here. So on the right, you've got this idea of the non-environment room, and it's a really simple idea. What you do is you flush mount the speakers on the front wall, and that avoids any reflections from the front wall straight away, at least first-order reflections. And then you just absorb everywhere else. Now, you do need to remember that you need very bulky absorption to make it operate across a very wide range. So you might actually get, with about 60 centimeters of absorption on either wall, you might get down to the low frequencies, the 200s, the 100s. It's again dependent on the wavelength. Of course, that takes up a lot of space from the room, and these rooms tend to actually kind of lose a lot of the studio footprint. Not an easy thing to do nowadays, especially as real estate is becoming really expensive. The other problem is these rooms sound a little bit oppressive. They're almost anechoic, and that's not a really nice environment to work in. So other approaches have tried, for instance, redirection of reflections away from a critical listening area, and then you need to decide what to do with them as they hit the back of the room. If there's a bare wall, you might get a nasty echo. You don't want that. You want to try and avoid it. You can either absorb them, again under the same principles. You might need very bulky absorption, or you can try and scatter that energy so that it comes out of the back room without the nasty kind of behavior. It's sort of spread all around. And then eventually it's going to hit these side walls, but by the time it reaches the listener's ears, it's already beyond that initial time delay, and they have lost a lot of their energy. Okay. And let's now move on to the third part, modal control. Now, I'll kind of stop and make a kind of a catch-up point there. We've looked at dealing with problems to do with reflections, and to some extent, I've kind of been suggesting that it's easy to do according to the principles of physics. If you've got, enough bulky absorption, you'll be able to treat the elements. If the redirecting surface is large enough compared to the wavelength, then you can redirect the energy. And if you have some kind of diffusion, like you can see in the back there, then you can scatter the energy. But as you go on to low frequencies, that's not so easy. For instance, the diffuser at the back of this room cannot do anything with waves of 5 meters, 8 meters, 10 meters, 17 meters, because it's just too shallow. So what happens in the low frequency part? First of all, remember that this is a really important part of the audio, okay? It's about a third of what we listen to. If the low frequency is not right, then you struggle to actually, produce good content. So it's important that we get it right. We're talking about frequencies between about 20 to 160, 200 hertz, where the wavelength is quite large. So I've got an example here just to give you an idea of what room modes are. And again, I'm expecting many of you to know what this is. So I've got a room, I've got a source placed in that room, and then I've got 2 listeners. And I want you to listen to the difference that each of these listeners is exposed to in terms of sound field. This is a simulation, but hopefully it will come through in the samples. So we're listening to the low frequency, the bass. And now here's what this chap at the end here, perhaps sitting in the sofa at the back of the studio, gets. Did you guys notice a difference? There's quite a clear difference. And we can see it here in these waterfall plots. So we can see the peaks of the resonances and how they decay. These are the decaying modes. And we can see that this is definitely a different kind of response to that, especially here in the very low frequencies. So what are these things, room modes? Well, they're basically standing waves that kind of get set up because of waves propagating within the room and bouncing off the walls and creating constructive and destructive interference between them. Now, we know that we can measure them in a spectral plot, so we can see what their frequency is. Here are the frequencies of the modes for a specific source, receiver, room scenario. We know, as we've seen in the previous example, that as you travel across the room, you go from zones where that particular mode is very loud, and zones called the nodal lines where it's kind of almost deaf. It's almost as if it's not there. Okay? So you've got a situation where some notes sound really loud, other notes sound really quiet, and as you change to another position in the room, the whole thing changes because of these parameters. And we know that in terms of sound, especially on transient sounds, it tends to cause a sluggish response. We start talking about muddy bass and things like that. Okay, so have a listen to these samples again, for those of you who didn't pick it up. So you should kind of hear a little bit of a resonance, the modes ringing in the later part. Okay, so what are the tools available to treat modes? Here we can't just bring in absorption, because at the very low frequencies we'd need to have like lots and lots of foam, start taking lots and lots of space. So some people have argued that you can splay the walls. You can kind of put angles on the walls to try and avoid the modes. This is something that's been published in a book called Recording Studio Design by a good friend of mine, Philip Newell. And they've actually simulated a mode in a given room of certain dimensions and plotted the spatial distribution. So you can see that in some cases we've got like very loud pressure, very loud sound for this mode. That's the dark regions. And then we've got the light regions, which represent the nodes where that mode is not very well supported. If we splay one of the walls of the room, the behavior doesn't really change. You still have the mode. Some things have changed, moved around a little bit, but you still have the mode there, and that's a problem. Another often argued idea is to change the aspect ratios of the room, to change the relationship between the length, the width, and the height of the room. And that's in an effort to try and avoid these ideas that modes bunch up together all at the same frequency, giving you a really large reinforcement at that note, and then no reinforcement whatsoever in between. And of course, this kind of grows. So you can look out for good, sort of called golden ratios that try and spread out this energy of the modes. And some people have published maps where you can go and select these room ratios. The problem is all of these simulations consider that you have the source in one corner of the room and the listener in the opposite corner. Now, we hardly ever put sources in the corner of rooms, but I don't know of anyone who actually listens by placing their head in an opposite corner or in any corner of the room. So this doesn't quite work, or at least it's not as efficient. Okay, so what can we do? Well, we can try and absorb the energy of the mode, and some of the research I've been doing over the years shows that this perceptually is actually one of the most efficient ways of controlling modes. So this is an idea of a mode before being absorbed, so this modal decay is really long, and this is after we've placed some absorption in the room. How can we absorb that? Well, there are tools called resonant absorbers that you can design, and they tend to have a design frequency, a frequency at which they're most efficient. If you design that properly and place them in the right place in the room, then the results can be quite striking. And this is, of course, much cheaper than splaying the walls or changing the dimensions of your room. So here's an example of a room that had a problem, and this is how it sounds. So you can hear that, the resonance in the low frequency. And after we place enough absorption at that specific frequency, then we see objectively the mode disappears and the sound changes a little bit. Okay, so what's the take-home message? Well, you need to treat flutter echoes, again, using the tools that are available. Always aim for an ITD in the control room which is longer than the recording room, again, using the mid and high frequency tools. And at low frequencies, you absolutely need to damp the low frequency resonances before the room is usable. And that's it. Thank you very much.